This is a high school geometry course, a lesson in triangles. We'll talk about various triangles, including isosceles triangles. First off, we'll review some of our previous information. Let's look here at this one. Okay. Can we determine that angle A is congruent to angle D based on the information given? Well, yes but no. Directly, we can't tell. However, if we were to find out, first prove that the left and the right triangle were congruent, then we would know that the corresponding parts of congruent triangles are congruent, and that would make A congruent to D. Well, can we get the two triangles congruent? We need one of our shortcuts. Remember, to be congruent, all angles and all sides corresponding, of course, must be congruent. We don't have that. We do have a shortcut, however, that might work. That's side, side, side. We have two sides marked with 1 as being congruent, two sides marked with 2 hash marks being congruent, and the third side, BC, reflexive property, is present in both triangles, so it's the same in both triangles. It's the same segment. So we do have side, 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 side. The two triangles are congruent. Double check that A and D are the corresponding parts. Yes, they are. They're the angle that join the ones marked 1 and 2. So despite the fact that it's a mirror image, A and D are the corresponding parts of those congruent triangles, and they are congruent. Okay, how about this one? Want to know if B is congruent to T? Of course, again, we'll have to do the same thing. See if we can find some congruent triangles. Well, we've got a bow tie here, and we notice that we have two sides marked as congruent with 1 and 2 marked with 2. The included angle between them is at P for both of them. Those are vertical angles, and they're congruent. So we have side, angle, side, side, angle, side. Remember, whenever you state that, state it in the order given. 1 mark, angle, 2 mark. 1 mark, angle, 2 mark. And so then it's only left to us to decide if Q and T are the corresponding angles. Yes, they're the one that's next to the one side and none. One side and none. Yes, they are corresponding. So they're congruent. How about this one? JM and LM. Well, we need to find congruent triangles because there's not enough here just on its own. So JM and LM. The hypotenuses, they're both right triangles. 90 degrees here leaves 90 degrees here. They're both right triangles. The hypotenuses are congruent. Notice that this leg is common to both of them. And so we have hypotenuse leg. The two triangles, the ones on the left and the right, are congruent. Then its left are JM and LM. The corresponding parts, yes, they are. And notice that it's cited correctly from the acute to the right, the acute to the right. So you wouldn't want to say JM and ML. Okay, it'd technically be wrong. Okay, how about this one? AC and BD. Okay, well, what can we do with this one? We have two angles and a common side. So the common side, you have a side and angle. We need another angle. With this side, the angle given will not be the included angle, so trying to find another side won't help us. It'll just be that wonderful side-side angle that makes a donkey out of us, and I don't want a donkey made out of me today. So I want to find another angle. Okay, parallel. We have that these two lines are parallel. Right here, parallel. And think of the diagonal as a transversal. So given that, we can see the angles in the triangle, that would be BAD and CDA, are congruent because they're alternate interior angles. Notice that there's no way to find the big angle at A and the big angle at D as congruent because the sides, the left and right, are not parallel, which would what be necessary. And the big angle at D is not the complete interior. Here's Ollie. Is not the complete complete interior angle. So there we have it. We have angle, angle, side, angle, angle, side. So they are congruent. AC and BD are the congruent sides, and notice that they aren't listed in the same order. AC should be DB, but we're not going to take off it. Not for this time. Okay. Here's this one. Okay, this one. Notice there's two overlapping triangles. That can kind of get messed up when you try to work with it. So there's ways to deal with that. And I want to mention something about this with regard to this one, but in general, with your development, the age that you're at, brain scientists tell us that there's a window of opportunity with regard to spatial reasoning. What do I mean by spatial reasoning? Spatial reasoning is the ability to take things and see them in your mind and turn them and examine them from different angles in your mind. Flipping things, twisting it, inverting it, that sort of thing. Kids that are younger than y'all really can't do it very well. And there's an opportunity of about maybe 2 years, something like that. The brain scientists tell us when the pathways are available to you and that you can increase your abilities with regard to spatial reasoning. And now is that time for you. And so I want y'all to practice and do it and do the best. Now, okay, everybody gets some and from their gene pool, from their parents, and some people get more. So some people have a better natural reasoning ability in spatial things, in 3 dimensions, and to do things in their mind and turn them around and that kind of stuff. Some people can do it really pretty good already, and some people can't. But during this, about a 2-year period in your life, this is your opportunity to make it better. If you're not very good, you can get up to good. If you're good, you can get up to great. If you really practice, you can get yourself where it'll really help you to be. And this will help you. It's something that you're going to need and that you need now. So I encourage all of you to put some attention in to doing this. I used to teach 7th graders, then I taught 8th graders, and the difference between the groups of, large groups of kids as to what they can do in their mind on this, it's really obvious to me that whoever the brain scientists that I've read on it are right, that it's when you're at the age that it starts, and it's right between 7th and 8th when it really begins. Okay, one way that you can help with this is to think of it with its component parts. So I'm going to draw out here the 2 triangles to help me see what's going on. So that's what I want for you to do to help you do it. And then label it the same way. So the one on the left is JNH with 2 marks at H. One, then draw the other one out separately. Okay. This is GKL. Okay. Drawing them out separately and labeling them just as they are in the original diagram. That'll help you see where the corresponding parts are. And notice on this one that they're mirror image relative to each other. So it can also be helpful to go ahead and flip one of them. I'll flip this one. Okay? So what do you see here? Now they're oriented just exactly the same so that you can tell which parts correspond. Now it's good for you to do this. Writing down the transitions here helps you order your thoughts and train your mind to be able to do it on its own. So I strongly encourage you, whenever there's a complicated diagram, to practice doing this. If you will write it down and not just do it in your head, although the ultimate goal is to be able to do it in your head. But don't just assume you're as good as you're going to get. If you don't practice, you won't get better. So please go ahead and practice doing these, okay? So then the next one. Oh, and that one was congruent. Here's this one. Look at that. Again, it might help you to draw them separately. Notice that they are flipped. Mirror image. Well, I guess depending upon how you rotate it. It is true, it does turn out to be. and this one is side angle angle, or angle angle side. So the two are congruent. Okay, let's look at an example here of a hang glider. Now, hang gliders steer better if the two sides are congruent. So this guy's going to be able to manage his hang gliding a little better if the two sides are congruent. We're drawing triangles in here, and we're given that angle 1 at Q is congruent to angle 2 at S, and the 2 at T are congruent. So, do we know that the triangles are congruent? Well, angle, angle, common side, reflexive property. Angle, angle, side, angle, angle, side. The two angles are congruent, so they'll have a pretty easy time, or at least he's got a chance of being able to steer it well. Another one. Okay, this is an old Boy Scout item, and if I remember right, it's one of the requirements for STAR. I was a Boy Scout, a merit badge counselor at one point. What we're going to do here is talk about what happens when you don't have your tech. Okay?
Here I am out in the backyard about to talk about how you can find a good right angle when you don't have any tech and you don't have anything to do it. So how can you do that on your own? Things like this would be how folks did it in the very distant past and how you can do it now if you find yourself in a tight. Okay, the problem that we're working on needs a good right angle, and it's out in the middle of nowhere trying to figure out the distance across a river. Okay, you could swim and get ready if you had a rope you could drag, or you could find yourself and use some geometry to do it. Find yourself a good right angle. Here's how you can do it. Okay, stand looking at, you're going to have a reference point. It'll be one of the angles that you're looking at on your little river. Okay, one of the points. You're going to look right at the reference point. I'm looking across at it. I'm standing straight with my shoulders straight. I'm not standing crooked like this or crooked like this. I'm standing straight looking at it, and I'm going to point at it off in the distance. Okay, everybody do that. Find something off in the distance, stand straight, right on it, point far away from it so it's right in front of you, not crooked, not this way. Change your whole body, not your head, so that you're looking right at it. Point at it. Okay? Then when you've done that, don't move your shoulders, don't move your head, don't move your arm. Take your other arm and put it straight out. Okay? So what we'll have here then is you can get yourself a passable right angle by doing this. Now don't do your shoulder like this or like that or whatever. Pay attention to what you're doing. Again, you'll be perpendicular, looking straight at one of your items that you're referring to, one of your reference points. Look straight at it, point straight at it. Take your other arm, put it straight out. Now, without moving your shoulder, without moving your arms, turn only your head and sight down your arm and see where it's pointing. Okay, when I'm looking there, it's pointing over there at a particular tree with red flowers on it. It's way over there, okay? And so now I have my first reference point, maybe a rock or something. I've looked straight at it with my shoulders straight, pointed straight at it, didn't move my shoulders, pointed my arm out, and looked and saw in the distance a tree with red flowers that I can remember what it is. I have a good right angle. Okay, this does not do it. We're not talking about this. No, 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 no. It's got to be one that's straight on and one that's out, perpendicular. That's how you get yourself a good right angle. And when you're out in the woods or out in the wilderness or out someplace and you don't have any tech, you might just need to find yourself a right angle so you can use your geometry to get what you need. Okay.
So here again is our problem. We want to find out how far it is across the river without getting wet and without any tech. If you have a compass, you can use that for a right angle, but otherwise you're going to find your good right angle using your body and paying attention to what you're doing. So how you would do that is one person would stand here and look here either at a reference point like a rock or a tree, let's say a rock, or a person. So if there are two people, they can both do the good right angle form the right angle here with their arms, find the right angle here with their arms. Okay, what do we have when we do that? If you just have one person, then you'd have to do it 2 times. Okay, go walk and do it. Okay, so what do we have then? We have 2 lines that are perpendicular to the same line, therefore they're parallel to each other. So NP and LK are parallel. Whoa, parallel gets us all kinds of things. It gets us angles here at P and L, the alternate interior angles. It also gets, we already had the right angle and we already have the vertical angle. So we know that the top triangle and the bottom triangle are similar, that all the angles are the same. But we want a distance. So to get a distance, we're going to have a length. We're going to have them congruent. Remember, if you've got at least 2 angles, all it takes is one side to find out how big the 2 triangles are going to be to make them congruent. Well, the one we can get here is the one right here, because we can walk from K to N. Okay? So what you do is you start at K or N and walk to the other. Count your paces. Count them up. If it's 140 paces, then come back at 70 paces halfway and mark some landmark there, or make a landmark or a big rock or something, so that you know where the midpoint is, so that these 2 are congruent, which means that NP and LK are congruent. How are you going to find out how long they are? You know that they're congruent, but you don't know what the measure is yet. Well, you can walk across the water, but that's probably not going to happen. Or you could come from K to L and walk that out. So you go to K, get your good right angle, see your landmark, in my case the tree with the red flowers, and walk towards it. Okay? You walk towards it until you can sight these. So the person up here will have said, okay, the tallest tree is the reference point that we're going to across here. The person up here sees that. That's where they pointed to with their right angle. So they have that one for a reference point. Then you know the midpoint. So you count your paces until it lines up, until you're lined up with the point across the river and the midpoint. When you get to the point that you see them lined up, then you know that you've gone the distance. You've counted it. Say if it's 210 paces, then you know that it's 210 paces across the river. And you say, well, paces? What's the good as a pace? I want to know feet or meters or something. Okay, believe it or not, your paces are remarkably consistent. If you're just walking normally, they're going to be the same. That's just how your body works and messes your hips up, I think, if it doesn't. But you may think, well, I don't always take the same steps, but pretty much you do, unless you're a girl wearing high heels. That's a whole other story. Don't that? Yeah, okay, anyway. So, they're going to be pretty much the same. Any of y'all who are who play wind instruments and have been in a band, if you've done any marching, then you already know this is true, how consistent your paces are. And if you do play a wind instrument and you go into high school, join the band. It's a lot of fun to go marching. You'll really like that, I think. Okay, it's hard to march if you're an oboe. Flute, you got to memorize your music. I play the flute. But it's a lot of fun, and I highly recommend it. What's the point here? The point here is your paces are remarkably consistent. Mine is about 22 inches from the same point of my foot to the same point of my foot. So I can take a whole bunch of paces, and I can come particularly over a longer distance, which tends to even out the irregularities. I can get it pretty good. Okay? You can do that too. That's how fence people do it. Anyway, it's remarkable. It's fun time when you just have anything to do. Walk up and down the driveway a few times or some flat place and figure out what your pace is, what your normal pace is. That way you'll know what it is and you can figure these things out. Okay, so that's how it works for that. Here's a challenge. This is kind of fun. See if you can look at it. I didn't do this in class. Take a moment and pause it to see if you can figure this out. And then I'll put the proof up. I'd like for you to give it a go, so pause it and see how you did. Okay, and here is a proof of that challenge problem. Look through it and see how you did. Now we're going to switch gears here. We're going to go to isosceles triangles. Yeah. Recall that an isosceles triangle by definition is one that has 2 sides that are same. And we understand that if it's 3, that's at least 2. So at least 2 sides that are the same length. Let's look at the terminology. If you would, draw yourself an isosceles triangle. Let's talk about the naming of it. First off, Isosceles was a man he was Greek, and he actually lived. So if you're talking about Isosceles or about the person, then you're going to need it to be capitalized. If you're talking about the triangle, if you're using Isosceles as an adjective, say it is Isosceles. In the American English usage, it's okay to use capital I or lowercase I. Doesn't matter. Both are considered correct. My understanding is that the British people generally always capitalize it. I tend to always capitalize it as well, but it's not a big deal. Okay, so it's isosceles. So by definition, 2 sides are congruent. The 2 congruent sides we call legs. Okay, is everything in a triangle a leg? Yeah, it is. But when we're talking about isosceles, we call the 2 congruent ones the legs. So since we're calling those the legs, then we'll call the one that's not the 2 that's the same the base. We have references to the angle. Of course, all of the angles are vertices, but we're going to call the angles that are adjacent to the base angles, cleverly so. So these are the base angles because they're adjacent to the base. One of their sides is the base. This one is not. This one is at the vertex. Are all of these vertices? Yeah, all of these are vertices. But in an isosceles triangle, we call the one between the 2 congruent legs the vertex. So this is the vertex angle. Okay? So that's our terminology. I'm going to get, you need to have 4 straight things. So here's some straight things that you might find in your house. Rulers, pencils, chopsticks. So pause and go find yourself 4 straight things that you can use to play around with triangles. Okay. Hopefully you found yourself 4 straight things. And I'm going to start with 2 things that are the same length. I'll use my little butter knives here. Okay, these are the same length. And are they straight? They're straight enough for what we're doing. Okay, they're straight enough. And so what I'm going to do is I need another straight thing. I'll use the edge of my Versatiles box here. Okay. So these will be 2 of my angles of these will be my congruent sides for my isosceles triangle. And this will be the 3rd side, the base. So these are the legs, and this is the base. My butter knife just happened to have a hole in the handle, so I'm going to use that to help me. So I'll put them together here right like this. Okay, got the light on it, funny. I'll move it over a little bit. Okay. So I have my 2 congruent sides and my base. Well, what I'm interested in at the moment is the angles. So take yourself a little scrap piece of paper and draw and trace the angle. Once you've done this, go ahead and make your angle. Okay, I'm going to put it right here, and it looks like my angle down my butter knife is about there, and across my Versatiles base is about right there. Okay, so that's the angle that is this base angle here on the left, made with the congruent side and the base. It's a base angle. Well, do that. Once you've done it, rotate it around and put it on the other base angle. Oh my goodness, look, they're the same. That's handy, isn't it? Okay, well, you know, the one I made just happens to be about equilateral. I wonder if that affects it. I wonder if it'll work for bigger ones or smaller ones. Well, I'm going to try a smaller one. Okay, I'm going to make an itsy-bitsy one here. If I can get my butter knives to cooperate. Okay, so there's a smaller one, much more acute vertical angle. Again, I'm going to take a piece of scrap paper and trace my angle. Okay, so there's my angle. My left base angle. It's the base angle, one of the base angles. Okay, once I draw it, I'm going to rotate it around and put it on the other base angle. Oh my goodness, it looks like it's still the same. Who'd have thought it? Okay, well, almost equilateral and really acute at the vertex worked. Wonder if really obtuse at the vertex would work. So let's give that a try. Really obtuse. Okay. Really obtuse. Okay. Well, let's see if that one works. Okay, I'll trace the angle with my butter knife and with my Isosceles case. Gives me that base angle. Turn it around, put it on the other base angle. Oh, yeah, it works! Look at that. The base angles are congruent. Clever. Now, we could call that the butter knife theorem, but I'm suspecting that you suspect that that's not what we call it. We call it the base angles theorem. Boring. Butter knife sounds better. But there it is. So please make note of this. Pause it if you need to. Now I'm going to notice what happens when they're not the same, just for reference. So if I have my butter knife, and then I have a dinner knife, which is a lot longer, I wonder what's going to happen. Okay. Do the angles stay, are the angles ever the same? Look. Okay, here's a big obtuse one. The base angles are not the same. I can tell by looking. This one's bigger. Okay. What if I move it in closer? It's kind of medium size. This one's really big, and that one's bigger. They're both bigger, but this one's still bigger than that one, relatively speaking. And, you know, I can keep on going, and I can do things like this where it gets really big and then starts getting smaller. But what you notice is the angles are never the same. The side lengths are not the same, and the angles are never the same. We'll talk more about that at another time. But I just want you to notice that it doesn't work when they're not the same. Okay, now, everybody get 4 things that are long and straight. For this one, I'm going to use chopsticks. Okay, so there's some chopsticks. I'm going to make an angle with my chopsticks. And I'll use a pair of pencils. Okay? I want the same angle. So I'll put them together like that to make sure I've got the same angle. Now this is going to be a little bit tricky. You might have to redo it a couple of times so that you can get it to work. So I've got the same angle, and I want, and I want to keep the same angle. I'm going to take my pencils and flip it around. Okay. But I want the same angle. Here's how I'll do it. Okay. I'm going to put it on top of it so it's making a triangle between the chopsticks and the pencils. It makes a triangle. Notice that it makes an isosceles triangle. Okay, what did I know this time? I didn't know the side length. I didn't start with the side length like I started with isosceles triangle. I started with the angle. I have a chopstick angle and a pencil angle, and they're the same. Apparently it's close enough for this. When I do that, look at the side lengths that are in the triangle. This one and that one. They look about the same. Looky there. Okay, I've got that distance right there. And I go over here, and it's the same. Cool. Okay, well, it worked for this medium-sized one. Will it work for a big one? Okay, there's a big one. Again, I've got 2 angles that are the same, or pretty close to the same. When I measure it, looks about like that with a little left over, about like that. But yeah, okay, that's going to be pretty much the same. If I were better at holding a pencil, it'd be exactly the same. Oh, that's what it is right there. Okay. What about a little bitty one? I come down here to a little bitty one. Is it about the same? Is it the same? If it were drawn well, it'd be the same. Okay. So that'll be about there. Oh, yeah. Okay. Cool. So what did I do? I started out with 2 angles that might be base angles. We can't call them base angles unless we know it's isosceles. The ones that are putative might be base angles, are the same. And guess what? The opposite sides are the same. How about that? When two angles are the same, the opposite sides are the same. And that's not the chopstick and pencil theorem. It is the base angle's converse. Notice it's the backwards one, the converse. So pause it and go ahead and write this down in your cipher. What happens when we have an equilateral triangle? Okay, well, when an equilateral, remember, you take two sides, so the opposite ones are the base angle. I just pick those two. It doesn't matter which ones you pick, they're all the same. So pick it to be convenient. But wait, I can turn it this way. Now I can say these two are the sides that I'm going to take as the isosceles congruent sides. So these angles are congruent. But wait, I can do it again. Now I'm going to take these two sides as the two sides that are congruent for it being isosceles. So the opposite angles are congruent. Wait, that just means they're all congruent, doesn't it? Yeah, well, that's just like one more step. And remember, one more step is a corollary. So the base angles theorem corollary is that if a triangle is equilateral, then it is equiangular. Write that down, pause it if you need to. Okay, well, what if I knew the two angles? What if I had this equilateral triangle, and so that means they're all equiangular. Let's see. By definition, we've had that before, but let's do it in this context. Okay, if I know these two angles are congruent, then I know the sides are congruent, which makes it an isosceles. Oh, but wait. What if I know these two angles are congruent? That means these two sides are the isosceles sides. Oh, but wait, I can do it again. What if I know these two angles? That means these two sides are the congruent for isosceles. And oh, guess what? The corollary to the base angles converse. The corollary to the converse of the base angles. The base angles converse corollary. If a triangle is equiangular, then it is equilateral. Go ahead and pause now and attempt to work this problem, and then I'll show you how to do it. So pause it and give it a go, then I'll show you how to do it. Okay, here is how I did the problem. I'll say a couple of things about it. Okay. I started with the left triangle, the right triangle, and then did the left one and went down to it. You can either just add them together. Each time I did it by adding up to get 180 with the triangle sum theorem. Okay? Let's do another one. Okay. To this one. We'll just talk about this one a minute. Here. Okay. This one's not possible. If you look at it, you see one base angle that's 3x and another base angle that's 7y. It just doesn't help you. There's not enough information there to do it. Make sure that you can see that that's the case. And then go on to this problem. This one's going to be a little bit more problematic. So pause and work through it. Then I'll put up how I've done it. Okay. Here's how I did it. Hopefully you were able to work through it successfully. Okay. Couple of notes. When you come down to do that middle common side, you're going to have a quadratic. And don't forget, if you have a quadratic, you have to make it equal to 0 to solve it. When you make this one equal to 0, you see that you have a common factor. Once you take that out, it's x squared minus 16, which is the difference of squares. If you don't know difference of squares, you need to learn it now. You need to learn the phrase. I know you talked about it and learned it last year in algebra. Make sure you're remembering the phrase and what it is. Okay, perfect square minus. Plus does not work. Now, there'll be a way to do it in Algebra 2, but now, difference of squares, and difference of squares is always going to be with a minus whenever it is. So, perfect square, subtract. It's factored by the two square roots and a plus and a minus. So the answer will have both. Now, if you forgot that it's difference of squares, go back to the basic always works I can factor. Remember, you need all three terms for that, so you need to put in the 0x. And it works out and it gets the same one. You'll recall that often when you have a quadratic, one of the answers will not work out. And you have to substitute them back into the original to make sure. When you substitute in both positive 4 and negative 4 into the side length, into the side, you'll find out that it doesn't result in a negative measurement, so both of them are good. Because you're going to square it anyway, it's going to be positive. Okay, next one up. Give this one a try. Okay, find the value of x. Okay, what is x? Pause it while you do it, and I'll go ahead and put up the new answer. Here we go. This is how it goes. Give that a look. This is how I worked it. See how that comports with how you worked it. Okay, and then one more example. That'll be this one right here, number 34. I'll make it big. Go ahead and pause it and work it out. This one gets a little bit complicated, and I'll give you an outline of how to do it. Pause it and work it. Okay. And then here's how I did it. Check that out to see how you did it. Make sure you know what you're doing. Okay, well, here endeth the lesson. I'll tell you that we have one paste in left for Chapter 4. Go ahead and paste this in your glossary at the next available place. And remember, once you've done so, to fill in the page numbers in your notes where you've put the stuff. Okay, well, there we go, and y'all have a good time.